So what we have, the introduction to nanostructure material and nanosensors. So here we will now give the brief introduction to these kind of materials, nanostructure material, because this was also part of this program when we declared this browser for this program, sensor technology, that is the broad area. Then we have the theme. So theme you already noted, we have the nanomaterials, sensor, nanosensors and devices. So this, and then we have different parts, and then course content was also available to you before you join this course. So then let's discuss a little bit about the nanostructures, material and nanosensors. So particularly I will cover this particular work. You can see this is from my group, and I am just showing in 2020. So there are, I think, 12 SCI publications, and then 2 are the proceedings. They are also SCI. So these all publications are 2020, and I will present mainly the nanostructure materials work from these publications. So 2020 only, I will not present the previous work. So and then we talk about the nanomaterials. So here you can see first we are talking about the materials, so, or materials tetrahedron. So materials and nanomaterials, there is no difference, there is only size difference. So let's understand what is material characteristic, or how we know about the materials. Because if you know about the tetrahedron very well, or anybody who knows this tetrahedron very well, or who understands this tetrahedron as good as possible, then you are this is directly proportional to your expertise in materials. So he becomes that good of material scientist. Here you can take.
Yes, sir.
Yes.
Sir, can I put in the PPT in the full screen mode?
PPT full screen?
Yes, sir. It's not visible.
Not visible. Okay, just wait. Sometimes it happens, then you have to tell me like this, so then I can stop this and then reshare. This is visible for anyone else?
In a slideshow mode, sir, then it will be visible to everybody. Slideshow is there, no, sir?
Now it's visible?
Yes, sir.
Now it's
okay. So whenever you feel difficulty, because sometimes it happens automatically, I am not changing anything, but then you please inform me. So it's good, thank you. So then we are talking of the material tetrahedron. So then you take about any of this vertex, like here processing. So the way you process the material, it changes its performance, it changes its properties, it changes its structure, and everything is centered at the characterization. So characterization is also very, very important. Then only we can understand what is happening. So then if you see the performance, again, performance is related to properties, the performance is related to processing, again is related to structure. So this, everything is connected in this tetrahedron. So that's the reason everyone, or I told, or everyone says that as good as you understand the tetrahedron, you are that good of material scientist. So your understanding of tetrahedron is directly proportional to your expertise in material science. So then we talk about the nanostructure. So nanostructure is nothing, just is the reduced size. And why we talk about the nanostructures? Because every materials, they show unique properties at nanoscale. So what are the properties? For example, we can consider some of properties here, like optical properties. So these are dependent, this is color transparency. These are the optical properties. And then we can talk about the electrical properties, their conductivity. So these all properties which are listed here, physical properties, for example, hardness, melting point, and chemical properties, reactivity, reaction rates. These all changes when we change the size. And how they changes, we can just take a simple example of melting point. So how we define melting point? Melting point is the temperature at which atoms and molecules start flowing. They becomes free. That means there's the breaking of bonds. For example, NaCl, sodium chloride, if you take. So what is the melting point for sodium chloride? So once you heat the sodium chloride, once sodium ion and chloride ions, they start becoming free. That temperature is the melting point. So what is the relation of that this means the temperature with the size? So if you take the large particle, means bulk, and you take small particles, so small particles you are making by breaking the large particles. So that means once you make the smaller particles, that means you are breaking the bonds. So number of bonds in smaller particles is less. So you need to break less number of bonds in the nanomaterials. Because of that, because you have to break less number of bonds, that means this ions will become free easily with with reduced energy. So that means melting point will reduce. So this is the universal phenomenon. So the melting point is expected to get reduced when you reduce the size. And then you already know the reactivity, reaction rate, this everything is dependent on the surface area. You also know this, when you reduce the size, you have more number of surface sites, you have more corners, more edges, and you do not have the many atoms which are inside. We have most of the atom on the surface. Because of that, the reactivity and reaction rate is higher. And then we talk about the conductivity. And then conductivity and transparency, you can see here. This is sunscreen cream. This is zinc oxide sunscreen cream. So this saves you everyone from UV light. And this is because of the band gap. Then because we know that any radiation, so like you can see towards my cursor, mouse cursor. So this is conduction band, here is valence band. So this is energy band gap. So if any radiation incidents on the valence band or this material, if the energy of the radiation is higher than the band gap, then this radiation will get absorbed. Why? Because this electron will get excited. This electron will get absorb this radiation, and this electron get excited. If this energy is less, then electron cannot absorb this radiation, and this radiation will transmit. So that is how material become transparent, or radiation becomes transparent for, or material become transparent for some particular radiations, and it absorbs for all other radiations. So when we say the transmittance, this is not universal phenomenon. It is dependent on wavelength. For example, many of you will know that silicon. So silicon, it just looks black. If you have seen the silicon wafer or anything, it just looks black because this is opaque to the visible radiation. But it is very good transmitter for this IR radiation. It can transmit IR radiation. So this is again transparent. So every material is transparent in some particular wavelength. So so when in common language we say, then we talk about the this visible range. So that is different thing. But material, depending on the wavelength, the material is transparent. So silicon is also transparent for IR radiation. Here what we see with these materials, so you can see here, so this large particle, they look white. Okay, and if you have small particles, then they just match the skin color here. So this is the benefit of having this zinc oxide nanoparticles in the sun.
ऑनलाइन ट्रांजैक्शन ही कर दो कि मतलब यहाँ जाना, पोस्ट ऑफिस में अकाउंट खुलवा लो और अकाउंट से फिर इसका ऑनलाइन ट्रांजैक्शन
mute your mic. Some participant I can hear. Yes.
Hello.
ज़्यादा सही रहेगा।
Hello. Hello. Sir.
जाना नहीं पड़ेगा कहीं पे भी।
Hello,
मतलब ऑनलाइन का ये होता है, जब भी आपके हाथ में पैसे हुए तभी डाल दिए।
Hello sir.
नहीं तो ये होता है कि जाएंगे निकलवाएंगे।
PPT not visible?
Yes sir. Right side already cutted.
Yeah, that's what the problem is, that I am just not maximizing it. Now it's visible.
Yes sir.
Yeah, so yeah, please do not request to make it full screen, because that's I cannot resolve this problem now. So because once I make the full screen, for me is visible. So slides are okay, and what is happening I cannot see. Maybe this chat box is open. Can you check now? Please tell me if this is visible.
No,
Right
sir.
side?
No, sir.
No, it is the right side.
Partially.
Again, right side is
Not visible. Now
This
it's
is
visible.
okay, sir. Just increase
This
the
is fine.
zoom.
Okay. So then let's keep like this only. So then we were talking about this. So smaller particles, they make this transparent, like this one. So that's why we have the zinc oxide sunscreen, and this absorption, UV absorption is totally dependent on the wavelength. So because the wavelength of zinc oxide and then titanium oxide, that is very good for absorbing UV radiation. So that's why these two materials have been used in sunscreen. They are already commercially available. And then we have the nanomaterials. Means we can talk about the dimensions here. So we can classify all the materials in these many categories. So we have 0D material here, we have 1D material, 2D material, 3D material. Once we say 3D material, please do not say 3D nanomaterials, because 3D, three-dimensional materials are bulk material. Once you say 3D nanomaterial, that means you are saying quantum dot. So quantum dot is 3D nanomaterial. And then there is a little bit difference in the dot quantum or this nano. But most of the scientists, they use these words alternatively. So like for physicists, they say quantum dot, and anyone else, they say nanoparticle. And physicists, they say nanowire. Physicists, they say quantum wire, quantum rods like this. And they say, other scientists, they say nanowire, nanorods. And then physicists for thin film, they say quantum well. And then others, they say thin film or thin disk, like this. So the terminology is a little bit different for physicists, because physicists, they use quantum. And so quantum is a little bit of different than the nano. The nano is a, you can say, is a layman's term. For example, if you have a 5-6-year-old kid, your son or daughter, and he or she asks you out of curiosity, what is light? And then you know many things about light, like light is electromagnetic radiation, you know is interference pattern, dual nature, this particle nature, wave nature, dual nature, many things about is a kind of energy. It has polarization state. You know many things about the light. But once a kid of 6 or 7 years asks the same thing, what is light? You do not like to use the things which are true. Rather, you simply say light is something which helps things to be seen, or with that help you can see the things, which makes things visible. That is the definition you use for a kid. And you know that the definition is not right, still you believe that that definition is perfect for that age. The same way, when somebody is studying these nanomaterials as a layman, so the book writers or anyone else as expert, they start saying that if you have size range from 1 to 100 nanometer, the material is nanomaterial. But that definition is just like the definition just now I told about the light. But actually the nanomaterial is a little bit different, because nanomaterial is defined by its quantum confinement or quantum effect or nanosize effect. So it is property dependent. So the size you can define with the property, like the size at which property change drastically is known as the quantum dot or quantum size, that particular dimension. For example, you please look towards my cursor. So property, this is the property, y-axis is property, and this is size. So when you are reducing size, property changing like this, and then suddenly it changes like here, drastic change. Okay, straight line, it becomes like this. So then it is drastic change, and then size below this will be known as quantum dot size, or quantum you can say. So if you see different materials, for example, cadmium sulfide, quantum dot size for cadmium sulfide is 4 nanometer. And for zinc oxide, quantum dot size is about 7.8 nanometer. If you talk about the compound semiconductor like indium phosphide, and then quantum dot size is about 50 nanometers. So quantum dot size is depending on the material, because property or change in properties that is drastic, that depends on the material. So quantum dot size definition varies. But if you check all the available material, you will not find any material which shows this drastic change in property beyond 100 nanometers. So that means 100 nanometer definition is a safe limit. So you can use this definition, like when size is 1 to 100 nanometer, material is called nanomaterial. But that is certainly not a very good definition. That is not the expert definition, as you understood, that is similar definition like light we already discussed. So when this quantum dot this effect is in one dimension, then you have here thin film, then it's a 2 dimension, then it is nanowire, nanorod, or quantum wire, quantum dot. It's all dimensions are confined. Then it's called quantum dot. So what you mean by confinement? You consider this 3D room. This is 3D room, and you consider every individual sitting in the room is like an electron. Okay, so how many directions you can move? You can move in all the direction, X, Y, and Z direction in this room. Okay, all the direction you can move. So electron can move in all the directions. So that means mobility is in all the directions. So electron can move. So mobility is not focus. So that will reduce the conductivity, because conductivity formula, if you check, that is sigma equal to NE mu. Mu is mobility. So charge carrier mobility. So because of all dimension movement, mobility will be lower, so conductivity will reduce. If you check thin film, so in this case, you have reduced one dimension in this case. So electron can move in this direction, because this is similar situation like if you are sitting in this room and the roof is coming down like this. Please look towards my cursor. So the roof is coming down. So how many directions you can move now? You can only move in X and Y. So the same thing happens for the electron. Okay, like this. So electron can only move in X and Y. So the situation is thin film. So that means electron is confined in one dimension. And then if you talk about the nanorod and nanowire, so that means this ball is also going this direction. So roof came down and this ball is also moving this side. And that situation is like this nanorod, and this one wall came, this wall came. So so that came now. There's 2 dimensions, they are confined. If you consider this, all balls, they're coming like this ball is coming, this ball is coming, this ball is coming. So all dimensions now they are confined. So this is the situation. How many directions you can move now? You cannot move in any direction, and this happens to the electron. When electron is not able to move in any direction, and this is considered localized, and this situation is known as quantum confinement, or the size is known as quantum dot size. Okay, so conductivity increases from bulk, conductivity increases in to this 2D materials, thin film, and this further increases in 1D material. So that happens, but this you already understood. This quantum dot size, the electron is confined, it is not available for conduction. Then we have in nano size, we have the property change. What kind of properties are changing? So we have dominance of electromagnetic forces, we have importance of quantum mechanical models. So in classical mechanics, we used to discuss in large particles, and then higher surface to volume ratio. So this also changes several properties. So what we have here, you can see many things they change. So what are those things? So that micro scale, if you want to see this, then you can just use the eyes, everyone can use. So macro scale particles, there is no problem, we can easily see them. And then once we go the micro scale, then we need optical microscope to see micro size particles. If we want to go further below this micro size, then or we reach to the nano scale, then we need electron and scanning probe microscopes. And if we talk about the models, then models also changes. Classical mechanics is very good mechanics or physics to understand macro scale particles, but once we go below or we reach nano scale or smaller particles, the quantum mechanics becomes very important. I normally explain this by taking the third law of Newton, that is action and reaction law. You can understand easily by that law. So the statement of the third law of this action and reaction, that is every action has equal and opposite reaction. So but if you in reality, if you check, the reaction only takes place once action happens. So that means there is always time lag between action and reaction. And or you can say in other words, reaction cannot happen without action. There is always time lag. And as a physicist or any other scientist, you cannot just trust anything which has happened with the time lag that can be exactly same. Or you can reframe the sentence, or you can say there must be negligible difference between action and reaction because of the time lag. And this difference becomes significant when we talk about the quantum mechanics or smaller particles. So that's why the Newton's laws, they are not valid, or they are no more valid in the smaller particles, or they are quantum mechanics, they are no more valid. And sometimes this is also called that the Schrodinger equation we have here, which is equivalent to the this classical laws or Newton's laws. So here in quantum mechanics we have Schrodinger equation. So whatever classical physics, or whatever we do with the Newton's law in classical physics, or we can say we cannot understand any problem without Newton's laws in classical physics. The same way we cannot understand any problem without using the Schrodinger equation. So Schrodinger equation is sometimes called Newton's laws for quantum physics. So this has that much of importance. Then we have the several things, the changes also, like large particles, we have the gravity forces, and then we talk about the smaller or still further smaller than the nanoscale. Then we have this strong nuclear and weak nuclear forces. In between we have electromagnetic forces. So simply we want to say that everything changes once we reduce the size. So, and then we talked about this particular example. This is I want you to understand the quantum concept we just introduced. I know many of you already know the quantum, and then we just want to understand this. When we talk about the density of states, if I ask the question, maybe a little bit confusing for engineers, but for physicists or should not be confusing even for engineers. Density of states. When we say density of states, without saying anything that we are talking about, normally you consider that somebody is asking density of states for electrons, even it was not told. So when we talked about the quantum size or quantum dot or anything, we still consider this with reference to electrons. This is not true. It can be any quantum particle. Electron is a quantum particle. It can be any quantum particle. So the quantum dot size can be for any. For example, phonon. Don't worry, I will explain what is phonon. So phonon is just quanta of heat. In physics, everything is quantized. We understood that everything is quantized. Classical is no more valid. So heat energy is not continuous. It is quantized. So light energy is not continuous. It's a quantized. It's a form of photons. Similarly, we have the phonons. So heat energy is also not continuous. It's a quantized. So the quanta of heat energy is known as this phonon. So, or they have the vibration. So vibration energy, you can see that is quantized. So then there are two particles here. One is this electron, another is phonon. I hope everyone understood what is phonon now. I repeat, phonon is just quanta of heat energy. Similarly, as you know, photon is quanta of light energy. So phonon is quanta of heat energy or vibrational energy. So now here in this example, we are taking two quantum particles. One is phonon, which is quanta of heat energy, and another is electron. And this example is from thermoelectrics. And what we have in thermoelectrics, the behavior is simply like a thermocouple. So in that particular application, we want to restrict the motion of phonons, and we want a very smooth flow for electrons. So this is the requirement for thermoelectrics material to be of very high quality. So how to do that? So material can be very high quality. So for example, these are the several techniques. So these are the superlattice structure. So then you keep your electrons, and here you keep the electrons, virtually you keep here. Please look towards this mouse. So you keep electron and phonon here. You already know what is electron, what is phonon. So sorry. So now you want electron to pass and phonon to be blocked. So phonon should not pass. That means heat should not transmit. Heat should not conduct. But electrons should conduct. But if you look the Widman-French law, which is in physics, I will say that what is this. So please don't be confuse this one if you do not know. The Bidman-French law simply says that electrical conductivity and thermal conductivity both are proportional. That simply means you cannot increase electrical conductivity without increasing thermal conductivity. And our purpose in this case is to increase electrical conductivity without increasing thermal conductivity. So that's why there are several approaches. So how they works? So now you can consider the quantum dot concept we just introduced. So now your electron is sitting here and phonon is sitting here. So now phonon should not pass, electron should pass. That is done by quantum dot size effect. Because if you see the mean free path or diffusion length is different for electron and phonons. So phonon can be blocked first. So diffusion length or mean free path for the gases normally you use. So that one is, so diffusion length that is higher for the phonon. So phonon will be blocked first because of that constant. So you design these different layers in a way that the electron can only pass, phonon can not pass. So that means the quantum confinement effect, whatever we understood, that works for phonon only. So that means quantum dot size, quantum effect, that is applicable to phonon, not for electron. So electron is not in that nano size regime or quantum dot regime. So electron is free to move and phonon is not. The same way you can define the quantum dot superlattice here, like single material, then you have dot here. So if the electron enters this particle like this, okay, or nanoparticle or quantum dot, again this is the nanoparticle or quantum dot for phonon, not for electron. So when electron and phonon both enter in this particle or this dot, this is not working as a confinement center for electron, so electron can pass, and phonon is working as a confinement center because of the dimension, and then phonon will be blocked. And that is the way you can just violate the Bridgman-French law. Just we stated that electrical conductivity and thermal conductivity both are proportional, and you can violate that law using the nanostructures. And then here you can see bulk and nano, this dots like here. So these are the dots like here. So again, these dots works as a quantum dot for phonon, not for electron. So if both electron and phonon enters in this dot, so electron can pass and it will confine phonon. The same you can do same thing with having the single grain material like here. So then you have electron and phonon again here. So the grain size is this designed in a way, you have designed the material in a way like this grain again works quantum, this confinement, that size for phonon, not for electron, and that way you can just use. I hope you understood the quantum dot now very well. It's not limited to electron. When you say quantum, it is related to a quantum particle, which normally you have understanding with this understanding with the electron, because everything is governed by electron. When we say the things, conductivity or anything, the electrons are in outermost orbital, so they influence all the properties. So always we think about electron, but there are other things they are influenced. So here we are talking about the quantum dot in reference to the phonons, not in reference to the electron. So now I hope that everyone understood. If you have the questions, you can also ask in between, or I can take question now if you want to ask, and then I will start the other part. Continuation. This is continuation. You can ask. So everyone is able to see the slides, and Miss, am I audible? So please write in the chat box. So I have to ensure in between. So okay. So okay. So then these two experiments in quantum physics, we understood that quantum physics is very, very important when we talk about the smaller particles, because Newton's laws, they are no more valid when we talk about the smaller things. Or nanostructure, we are talking about anything you talk about the sensor or anything, when you are in a smaller size, that quantum physics becomes very, very important. And here I will discuss these two experiments very quickly, so you can have how amazing the quantum mechanics is, quantum physics is. This is just for your curiosity if you do not know. So double slit experiment, this is Young's double slit experiment. The only thing what you are doing, you are changing that light with the electrons. So if you do that experiment with the electrons or electron beam, then what will happen? You will have the diffraction pattern. That means electron is also a wave. The simple this one explanation that electron is wave. But what happened in this experiment? This one. So single electron means if you consider electron as a wave, that means a single electron is passing through both the slits, because wave only can pass. The Huygens principle, you remember the two slits, then the wave is, this light is coming, this is dividing in two and then interfering, and then you have the interference pattern on a screen. But if an electron is going, how it can give interference pattern until it's not passing through both the slits together? Then if it passes both the three slits together, then only it can give the interference pattern. But it gives the interference pattern, it passes through both the slits together. Okay, so there is a long story about this. Einstein was not convinced about this phenomenon, but it is true phenomenon. Electron passes through both the slits together means the same time, and it gives the interference pattern. We will not go into the story. And then the quantum entanglement is again a very interesting phenomenon. It says two interacting particles, quantum particles, they keep interacting even you take them away by far distance like galaxies. If you take them away like galaxies distances, then also they keep interacting. And that is also not very well taken by Einstein. But this phenomenon is also true. And then what is the problem in the common understanding? These experiment or quantum entanglement that create problem in the common understanding, like you have two interacting things, quantum particles. If you take them away, for example, electron spin you take, one is up and another is down. So if you take them apart, so that means spin, this one first electron is spin up and second is down. So if you take them apart, so then this first electron is spin down, then the second one will be spin up. They will keep interacting. So they will, so like this. So that is the meaning of this entanglement. So they keep interacting. And if you take them galaxies away, so the Einstein's question was, what kind of force is interacting them? This must be a ghost or ghostly force or a spooky force. And scientists told them that, yes, it may be, you can call this a spooky force. That is called the spooky external distances. We also name this phenomenon. But these phenomena are true. We have the quantum computers, we have quantum satellites, everything is working very fine, and everything uses this effect. So that means there's no problem in the concept. So then we have the some of synthesis techniques. So then physical vapor techniques for synthesizing these nanomaterials, nanostructures. So how to understand this? So you can see here. So we have many techniques which are vapor based, and you can make nano materials using those techniques. So if you have used any of the techniques, so then it's very good to understand other techniques. For example, thermal evaporation. Every technique, every vacuum technique that has 4 components. What are those 4 components? That is, you should have vacuum chamber, or you should have vacuum, and you should have substrate. You should have source material, okay, and you should have energy to make atoms or vapors of the source material. Source material, for example, you want to deposit gold. You may want to make nanoparticles of gold. The gold is source material, and substrate is where you want to make it. You want on glass slides, then glass slide is substrate. And energy is what? What kind of energy you are giving? So you are giving thermal energy, you are giving electron beam energy, or you are giving this mechanical energy, or you are giving laser energy. So what kind of energy you are giving? So almost all systems are same. Okay, what is the difference? The difference is what kind of energy you are using to make atoms or vapor of the source material. For example, you want to make gold nanoparticles. So, and you are using thermal energy. Then this process will be known as thermal evaporation. So, and then you can, if you are using electron beam to evaporate or make the atoms and vapor of some particular material, then that technique will be known as electron beam evaporation. So the only source, energy source is different. So that means if you know operation of one system, you can easily know the operation of other systems. Then why we have several techniques to making thin film or nanomaterials? Why we can't simply use one technique? So if you check in that way, so all the elements in periodic table, if you check, the metals are normally they have evaporation point below 1000 degrees centigrade. So that means they do not require very high energy. So metal can be evaporated at a very low energy, and that so the thermal evaporation is very good technique for metal evaporation. If we talk about the oxides or ceramics like zinc oxide, magnesium oxides, they require very high energy because their evaporation point is very, very high. That is about, in general, you can say all oxide material, they require as high as means energy to means their evaporation point is as high as 3000 Kelvin. There are exceptions like molybdenum trioxide that evaporate about 600 degrees centigrade. So in general, we are talking about, so all the ceramics, they or oxides, they evaporate at very high temperature. So the techniques such as E-beam evaporation, sputtering, magnetron sputtering, or laser ablation, they are very good technique. Thermal evaporation is not considered a very good technique when we talk about the depositing or making nanoparticles of ceramics by using physical vapor deposition. Again, we have many techniques and they give the different properties. For example, thermal evaporation if you are using, then we have like this, we can compare E-beam evaporation we are using. In this case, this deposition rate is this slow in comparison to sputtering. Sputtering deposition rate is high. So because of the high deposition rate, this film is normally amorphous. In E-beam, you expect film to be crystalline. The crystalline means systematic and periodic order. So that means in the E-beam evaporated thin film, atoms and molecules, they are arranged in systematic and periodic order. That is the crystal. And then sputtering, they are not arranged in systematic and periodic. Normally, they becomes amorphous. Okay, because the rate is high, deposition rate is high in sputtering. And you can simply consider with the students in the class. For example, you consider you have 50 students in your class and you have 50 chairs. And you ask your students, they are all sitting, and you ask suddenly to go them out for a few minutes. And then you give the 15 seconds time to settle. You say again, okay, you can please come in now. And you have 15 seconds or 10 seconds to settle. So in that case, you have given very less time. That means the influx is very high. The rate of incoming atoms or the students is very high. So what will happen? They will not, or they cannot take the individual seats. So what will happen? 2 or 3 students will reach to the one seat, and then maybe more, and then few seats will be totally vacant. And this order will be amorphous. This will be totally this unsystematic order. This can be totally compared with the amorphous order, and because this is happening because of high rate. And if you slow down the rate, if you say, okay, you have 15 minutes to settle down, then all the students will get individual seats, and then this will be perfect order. So then you can get, so the same thing is happening here. So thermal evaporation is giving you, or E-beam evaporation is giving you this ordered film, and sputtering is normally giving you amorphous, but you can still make it crystalline by post-processing. How you can make? You can make post-processing means heating that. Why this? By heating, atoms can again move to the other place. Why? Because heating means KT. K is Boltzmann constant and T is absolute temperature. So if you are heating something, that means you are giving KT kind of energy. Okay, so that energy can move the atoms and they can settle to the proper sites. Why everything settles to the proper site? Why nature likes to be in order? If you do not understand, if you do not have this information that nature likes everything to order, then it will be good information for you. Nature likes everything to be in order. When this order is disturbed, it does certain changes to get or regain this order. So when we heat the crystal, these atoms will move and they will move the proper sites, and then everything is governed, this order is governed by minimizing energy. Because those proper crystal sites are the minimum energy sites, that's why atom will move. So always driving force is minimizing the energy. So for example, if you consider the winter situation, if you have blanket you are inside the blanket in the winter time, and suddenly someone snatches your blanket, and then what kind of shape you have? And that question Miss teacher used to ask in the elementary classes. So what kind of shape you will have is a winter and somebody snatches your blanket, then you have, so this, you try to be a sphere. And what is the reason to you try to be a sphere? You try to be a sphere because for the known volume, a sphere has the least curvature area, least surface area. So surface area is less, so that means your radiation loss will be minimum. So everything is happening in that order only. For example, I will give you another example for energy minimization. So why everyone dies at last? Because see, if somebody is running, okay, so then he or she cannot keep running for longer time. If you just ask him or her to just stop, just stand, they will feel relaxed because energy requirement will be minimized. Once you ask them to stand for longer duration, they cannot keep like this. You just say them, you sit down, then the energy requirement will minimize further. If you ask them to lay down, you ask them to sleep. So everything this in the order, this requires minimum, less energy. So that is more stable position, more stable situation. And when this energy is not sufficient to run the system, which the minimum energy is required to run our body, so several functions are happening, and that's everything. That's everyone dies at last when energy is not sufficient. So everything is governed by energy in nature. So it can be social or anything scientific, but everything is driving force is always energy. So you understood all the techniques in this case. So only energy is different, and then we have sputtering techniques. So these were the vacuum techniques. Then we can have other techniques. They can be solution-based techniques, or they can be vacuum techniques are considered very good techniques. They give very high quality material. But we can have alternate techniques which can give you same kind of material. For example, we have this discussion, we have perovskite nanostructure material, and they have not been synthesized by this vapor phase techniques. Again, I repeat, vapor phase technique are the best techniques for quality of material. But we can have the same quality of material with the other techniques, which can be easier or cheaper. In this particular case, we are talking about the nanostructure material of the particular perovskite nanostructure material, and this is not using vacuum technique. This is using other technique, which is hydrothermal or solvothermal technique. So hydrothermal and solvothermal technique is nothing but just you can compare like a pressure cooker. So you have a stainless steel vessel. Inside that you put this Teflon beaker, and then you seal it, and you perfectly seal it. You have the solution inside that autoclave, that the Teflon beaker, and then once you put this in the furnace or temperature, that means the pressure inside will increase like a pressure cooker. So we know this how pressure cooker works. So then temperature requirement reduce. So that means if you use hydrothermal or solvothermal process, the conventional synthesis which you used, the temperature of synthesis can be reduced. For example, if synthesis temperature is about 600 or 700, that temperature in hydrothermal process can come down to 100 or 150 like that. So it can be reduced drastically. So this can be low temperature synthesis process, and it's not very expensive. It's simple, cheaper process. And then we have synthesized many materials using this process. So the hydrothermal process, and the other cheap process is sol gel process. Even you do not need pressure. You just make solution and then do the processing in ambient, and that way you can also get the nanostructured material. So that process is also that process is even easier than the hydrothermal process. So that will also be learned. So then this particular class of materials we are talking about. So let's study a little bit or understand a little bit about this material. So this is nothing like perovskite is nothing, is not a confusing word. So don't be confused if you do not know. It's just a Russian scientist, Perovsky. And he discussed, or the German scientist was studying this particular materials, or you can say especially CaTiO3. That material he was studying, calcium titanate, CaTiO3. And then in respect of the Perovsky, the scientist, this German scientist named that particular material, that structure, as a perovskite structure. So any material which is having similar structure like CaTiO3, those materials are known as perovskite materials. So that formula is CaTiO3 in general, or you can generalize that one. You can say MnO3. So M is Ca and N is Ti and O3 like this. Then you can have double perovskite material. So like this M site you have two elements, and N site also you have two different elements. So that way you can say double perovskite. So this is simply 2 units and like this here. So this is not a confusing, and they are very important materials for various applications. That's why these materials are very important. And we have done the paper which I showed you, that we have done recent work. So this is the sum of the recent work. The recent work on double perovskite for electrochemical performance. So that was in 2015, first paper on double perovskite that appeared. Then 16 we have paper, 18 and 18 we also joined this race. We did a lot of work on the double perovskite material for electrochemical performance. So then these last materials, they are not ours, but we first publication we also have in 2018 on this material. So these are the particular materials which we include in this particular discussion. These are double perovskite materials. So on this, so we will synthesize nanomaterials and we will discuss some of things. So, and then for any other work like we have, so what was the motivation? So we should have the motivation for starting some work. So motivation you can see here. This so first report on these materials, and this particular double perovskite like La2Cu MnO6, La2Zn MnO6, and La2FeCO6. This is the first report that means synthesis and electrochemical behavior of this. So this is certainly interesting. Then first report on solvothermal synthesis, and then again it becomes interesting. Then first experimental report on this nanorod via solvothermal process. So experimental report means this compound was predicted theoretically, but experimental study was not available. So we have synthesized this, and then we also did the experimental synthesis, another experiment on this material. So this is first report on experimental study as well as synthesis. Then we have first report on solvothermal synthesis, hydrothermal, for these particular materials. So, and then objective simply for any study, you design according to the research gap. So we try to find whatever the current research and where you want to go. So you decide your deliverables, you decide present status, you have to do deep literature survey. So after intense literature survey, you decide your deliverables. Whatever in between, that are the objective. So you have the route, or you have the route to, or a way to achieve this through these objectives. So you can reach to the deliverables. So that research gap you are trying to match, and that is known as objective. And we did the same thing here, you can see. And then characterization tools are basically here for the nanostructure characterization. And then these two first materials, as you can see, XRD. And what is XRD? So here you can see this one peaks. I can explain in this picture, then I can go fast. So this, why you get to the peak. So in crystal, what we have systematic and periodic arrangement of atoms. So you can consider, like again look towards the cursor. So like here we have systematic and periodic arrangement of atoms, like these atoms are arranged like this. So this will look like line. And then another one like this, systematic arrangement. Because on this particular 2D screen, we can only make 2D crystal, but crystals are really in 3D, real crystals are 3D. So that means one dimension you can consider perpendicular to the plane of the screen. So that means every line, which is looking line, is a plane. Okay, so every line, and spacing between these two planes is interplanar spacing. So when X-ray incident on this, so if you go back to the discussion of the double slit experiment, so it may be difficult to recall, and this was in school. So then you have double slit experiment, and then light was coming, and then you have interference pattern. And there you were not discussing about the diffraction pattern. And then later in the other chapters, we studied the diffraction pattern, even with the single slit. Even single slit was able to give the diffraction pattern. Diffraction is nothing, bending of that ray. and that can interfere later with the original ray and then bended ray. So that is the diffraction pattern. So diffraction is interference obtained because of the diffraction. So diffraction, this ray is involved. So what happens in the X-ray? So when you talk about the two slits, and why diffraction doesn't take place, because that require particular order, how the separation should be. So if the separation is of the order of the wavelength, then we have the diffraction pattern. So X-ray wavelength is the same order, whatever this atomic separation we have. Okay, interplanetary spacing we have. So that means X-ray is very good technique to study these crystals. So we can know. So when we have these atoms arranged in the systematic order or planes, we have this one. So then one ray will come, other X-ray will come, and this diffract, other ray will come, other plane will diffract. Then we will have part difference. And then once this part difference is equal to n lambda, which is condition for constructive interference, so then we will have peak. So the peaks are appearing because of the constructive interference. Wherever we don't have the peaks, there is a destructive interference. Again, this crystal arrangement, systematic and periodic arrangement of atoms, ions, or molecules, this is different for different crystals. So that means we will have a different signature, different peaks for every element or every crystal or every compound which is crystalline. So that means we can easily know whatever this compound is. So then, because signature will be different for different crystals. So that is how we know the crystal structure. So the XRD is used in all the studies to know the crystal structure. Here we have done the same thing to know the crystal structure. And then we have BET. This BET technique is named after three scientists, Brunner, Emmer, Teller. So Brunner, Emmer, Teller. So that is BET. So that technique. So here you can see this, any inert gas is used. And so like, again, you go back to your understanding of the nano powder. So that means you have powder. Okay. So you can look towards the cursor. So you have powder here. So now you have inert gas. So inert gas you try to allow to interact with the powder. So what will happen? The open area, wherever there are sites or the pores, so this nitrogen or helium or any inert gas, that will adsorb on those sides, but that will physically absorb, not chemically absorb. So once you heat it, then this gas will dissolve. So what will happen in this particular case of this material? So this gas will absorb some particular volume and then it will reduce. So this whatever you are measuring here, volume adsorb and relative pressure, that will give you hysteresis loop, and that way you can know the pore size. Pore size means when these particles come in contact. Okay. I want to make sure if slides are visible. Okay. Okay, so then here we can know the pore size. So here we can, like, particles are interacting. So like two particles are here. So like these two atoms or whatever you say, they are not atoms here, they are particles. So many atoms, they make the particles. Crystal structure, we talk of many things. So let's don't be confused. If we are confused, then we can ask for explanation anytime. So we are talking about the particles. So then these two particles, they come close like this. So if the surface is touching each other, so that means this area becomes ineffective. So that is not available for nitrogen or helium adsorption. So effective area is which is open. That is known as pore size. So pore size we can calculate. And then there are different kind of isotherms, and particular pore size when it comes to 2 to 50 nanometer, this is not a mesoporous material. In this case, we have tried to make all the mesoporous material for the electrochemical application. And then this is another XRD, and this is TEM. Here we have the pore. Here, the TM, this is 10 nanometers. So you can see the pore size must be smaller than 10 nanometer. And then here we calculated surface area. This is 32 meter square per gram. So that's, and then you can see this rods here. So then here you can see these particles are connected, and this kind of morphology helps for electron conductivity. So this connected particles should be connected so the electron can pass through easily. And this you can see these are particles, and you have the hollow area in between. So that can here there is electrolyte, or you can see this increases the pore area, pore size. So that is very good. And then pore should not be very high area. It should be smaller. It should be, but this particular application it should be in mesoporous size. That means 2 to 50 nanometer. That range should be not higher. So that provides very good morphology. If you this particular application, if you target, then rod kind of morphology with pores, that is considered ideal morphology. And you can see here with the zoom view, you have particles here. You can see clearly, and then we were able to synthesize these particles. And so this is nanostructure material we are talking about. And XPS, this is another technique. So when we talk about the nanostructured material, so till now, if you are not knowing before, you understood that surface becomes very important. And surface properties also changes. For example, XPS, this is X-ray photoelectron spectroscopy. And this is called very good technique, very good surface characterization technique. And why it is called very good surface characterization technique? Because it gives information from top few layers. It does not give the bulk information. It can give you as precise information about the surface as only including top few layers. And then again, same time, it is called very wet technique because it gives surface information, and surface can easily get contaminated. For example, any surface, to get carbon contamination, it takes 10 to the power minus 9 seconds. And that's very small time. I repeat, any surface can be contaminated in 10 to the power minus 9 seconds. So that means every surface, if you take out from the vacuum system, it will get contaminated with the carbon in this contamination. So that was the reason is many times it's called very good technique because it gives surface information, and then it's called same time bad technique because many times it may happen that you are getting information only from the contaminants, not from the surface. So what kind of information we can get from XPS? This gives core level information. What does it mean? So I just revise a little bit about the electronic structure, which is Bohr model dependent. So we have the nucleus, and then we have electronic structure. What is that? That nucleus, then we have 1s2, 2s2, 2p6, 3s2, like this outer electrons. So this gives information from the closest orbital. That means it tries to give the information from 1s2. So what happens in an X-ray, the incident on the material, and it take out electron from the inner core. That means near to the nucleus. So it can take, but because if you have the large atom, there are many orbitals. So it may be difficult to have that much of energy. Then we have electron from the little bit of outer cell. Like here, if you see binding energy EV. Okay, so the first one is for lanthanum. So lanthanum, we are considering what we are considering 3D orbital, because X-ray photon which we are using not having that high energy that it can take an electron from 1s2 orbital. But once we have the smaller orbital, a smaller atom like this is oxygen. Oxygen is not having many electrons, so not many orbitals. So it is possible to take the electron out from 1s with the help of X-ray. So then we can still study 1s. So the larger elements, larger electron elements, we have to take information from some outer orbitals. That is because of the energy. Otherwise, this technique is to get the information from the core levels. So core levels, you already understood, the levels which are close to the nucleus. And what kind of information we can get? We can get about the environment. Like if you have Ti atom, okay. So Ti atom oxidation state is 0. Or metal, Ti metal you say rather. Ti metal oxidation state is 0. But if you have Ti ion, say Ti 4+, that means you have already taken out 4 electrons. So if you want to know the binding energy, what you are doing, you are taking out the electron. So you have Ti0 and Ti4 plus. So if you want to take out one more electron, which will require higher energy, because in this case you have already taken out 4 electron, Ti plus, this 4 plus. So that means it has positive charge. So this will have more attraction force for the electrons. So you certainly need more binding energy for Ti4 plus. And then in comparison to Ti0, you need less binding energy. So that means you can study oxidation states with the help of this technique. So if you have this lanthanum is a +2, +3 or La0, so you can easily know, because these peaks will shift, binding energy peak will shift according to oxidation state. So, and this case is a mixture. So then you can know what kind of state is this. Okay, so this is considered very good technique, because surface oxidation state is normally reduced. For example, I give you example of magnesium oxide. Most of you will be convinced that magnesium, this oxidation state in magnesium oxide is +2 and oxygen oxidation state is -2. But if you do XPS study, means X-ray photoelectron spectroscopy on MgO, then you will end up with magnesium having, a lot of magnesium having plus oxidation state, a lot of oxygen having -1 oxygen state. And this happens because of the broken bonds on the surface. So this is totally possible for all elements to have lower or reduced oxidation state on the surface. And then we can study that one, and with the help of the XPS. And then surface, again I repeat, surface becomes very important to study, because all the properties or most of the properties, they are governed by surface. And XPS again is not giving bulk information. So if you have a compound determination with the help of XPS and the XRD, XRD is a bulk technique. So if you get the different information, different compound, FeO by XPS and Fe3O4 by XRD, it is totally possible, because you should remember that information which is given by XPS, that is on surface, and XRD has given information from bulk. So that this is totally possible. So this again, we use this one for the technique, and then we have this chemical CV curve, and then oxidation and reduction reaction you can know, and then this is charge discharge cycle. This gives again drive data, which is you have the specific capacitance and stability that can be determined. So this is again for the second compound, and then if you compare this for this particular study we did, so then you can see this is reference and this is our work. Some of its data is not available, so you can see these two compounds, whatever we studied, stability is very good. Okay, here, and then surface area is also better than the previous one, and that's the reason specific capacitance is high in these particular cases. In our cases, two materials we studied, and then we have another material. Now I will go a little faster. So then you can see the XRD, you understood the purpose, and this is TM is showing this these lines. They are okay. So TM, I will explain this why we do transmission electron microscopy. So transmission electron microscopy, we do to know many things. Like the first is to know the size. So again, in the transmission, electron has to pass to the other side. So that means sample need to be very thin. So transmission electron microscopy is very good for nanomaterials, because electron can easily pass to the nanomaterials. If you have bulk material, you cannot do electron microscopy. You have to use special sample preparation techniques, and they are very expert techniques. This is not possible for everyone to make the sample for bulk samples, or TEM samples for bulk samples. But there's no expertise required, or very less expertise required to make samples for STM, so this TEM analysis for bulk, so nanosamples. Nanosample doesn't require any high expertise. So what kind of information we get? One is the size, and then second information is crystallinity. So if you have a single crystal, then you get dot kind of patterns like this, 1 dot, 2 dot, like this dot kind of pattern you get. If you have polycrystalline material, then you get continuous circles like this, circles, one center and then circles. So that happens with the polycrystalline. This is, I'm talking selective area diffraction. And once you have this arcs and circles, you have arc like this made of circles, made of arcs, then this is textured material. And if you get only single diffuse ring, you have only one ring, not multiple circles, only one circle, one diffuse ring, then material is amorphous. And again, this VET analysis that has been done to know the surface, to know the pore size. And then we have this again pore size analysis. Here you can see the distribution of the pores. And then the second material, again you can see the morphology, and we were able to control this morphology. And then this rod kind of morphology, and then we have pores like this. So okay, so then this high this resolution, you can see this pictures further zoom, and then this is selective area diffraction. You can see here this dotted kind of things, that means the textured material. And there's a textured material is nothing, again don't be confused. So like powder, you have all the planes oriented in random order. So textured material means some of the planes they are missing, or the material has been oriented in some particular direction. In these kind of structures which are nanorods, and this is expected that material becomes textured, because this is not random distribution. So in this case, crystals are arranged in some particular direction. So if you have anisotropic shape like nanorod, disc, or thin film, anything that made of the nanoparticles, so anisotropic the shapes, they may lead to textured structures. So here also you can see this, the rings are not continuous, they are a little bit of broken rings. So this shows textured material. Okay, if rings are continuous, that means that shows the polycrystalline material. If you have dotted that pattern, that shows that you have single crystal. And then if you have one single diffuse ring, that means material is amorphous. So those are the various signature. And again, TM, this XPS has been done to understand the oxidation states. And why oxidation states are necessary? Because you can see oxidation and reduction reaction. In this case, electrolyte was KOH. So you can see the oxidation and reaction, how they are taking place. So XPS help us to decide about the reaction. That is very good study. And then we have electrochemical analysis again for this material. I will go a little faster now. And then we have nano-assembled nanoporous rods for this. You can compare this one, our study in literature. So you can see this La2 NiFeO6 like here. So you have the surface area here in comparison to other, you see. And then we have this specific capacitance here. And then it is not highest, but it is comparatively higher than many other materials. And these materials, they have oxygen deficiencies, and so they have that region. And some of the cobalt is there. So cobalt is also better material, cobalt based, but cobalt is toxic material. And then this research is surging towards getting this cobalt free materials. So, and then oxygen defects like this, oxygen deficiency, that can create further quality enhancement. So then we have mesoporous nanorods. Again, XRD is for the same reason. So till now, what we understood in this particular application, we should have the proper crystal structure. So we can control the crystal structure by different doping of different elements. So then that decides the properties will be higher, the behavior will enhance, the electrochemical behavior. Then the second one is we need proper pore size. So that means morphology need to be controlled. Okay. So then this crystal structure and pore size, this becomes very, very important. So this one, and then this obviously the size, nano size. So this is another material. I can see this for this material also we were able to control the morphology. You can see here. Okay, and then you zoom further. Then this is in nanometer, 10 nanometer. You can see the pores further, and this one, and then again is a texture material. And texture, you understood, is totally possible to be this dotted arc, because this anisotropic morphology. So these crystals are not randomly distributed; they are particular oriented, particular direction. So this is totally possible. And this is here you have the atomic planes and this separation. So this is measured 0.26. It may be not visible clearly, but if you zoom, then it will be visible. So this XPS, again, you understood the reason to know the oxidation states, like Mn and Ni is here, Sm this one. So what is the oxidation state? So you understood this Ni. So NiOH. So Ni is +2 and +3, and Mn is variable oxidation states. So it can go +2, +3, +4. So again, electrochemical analysis for this particular Sm to NiMnO6. You can see charge discharge cycle and stability is calculated again. So this is specific capacitance, and then we have energy density and a specific capacitance here. Okay, so and stability is here, you can see 86% stability here. So after this much of cycles. Okay. So then we have nanoflakes, and we synthesize this, the same hydrothermal process, and this is the flakes. Flakes, they are, that means it's a 2D material. Flakes are 2D material. So you are still working in one dimension, which is confined. So then again, mesoporous material. So it depends. Mesoporous, again, I repeat, mesoporous is called when size is from 2 to 4 sizes from 2 to 50 nanometer. So that material is mesoporous. And mesoporous, so I repeat, what kind of material was required for this purpose? So control this slide size, sorry, crystal type, and then control the crystallized size, and then control the morphology, and then pore size. So these are the main consideration in this particular material. So that material was designed accordingly. And XPS, this peaks have been fitted by XPS peak fit software to know different concentration of oxidation states and elements. Electrochemical analysis, again, to know the specific capacitance and stability. And this again, La2Zn046. This is another material. And then we have mesoporous, this Di2Mn NiO6 material, and XPS purpose, this X-ray purpose, you understood XRD pattern, that to know the crystal structure. And pore size, BET is for pore size analysis. This is pore size distribution. You can know from how much pore is varying. Like here, starting from here, it's the highest number of pores of this size, and then they are reducing. And this particular morphology is different than the whatever we discussed till now. And this morphology is also interesting. If you see these spheres, you check this one. These are microspheres. They are large size spheres, but they are composed of the nano features like this. And these spheres are hollow. So that means electrolyte can diffuse in this bus. So they work a mesoporous, you can see. These are still mesoporous spheres because of that particular feature size, and then because of the space in this one. They are not solid. These spheres they are hollow spheres, and they have all pores in this one. You can see the design here. So the different magnet. So this is also a desired morphology. This is elemental mapping, and this elemental mapping is just showing the homogeneity of the different elements. So in this particular case, we have Di, Ni, Mn, and O6, 4 elements. So this case, Di, you can say Ni, Mn, or and O. The 4 elements, how they are distributed. So then you can compare. This element is here, this way distributed, other is distributed in this way, third one is distributed, fourth one is distributed. That means you can see the distribution pattern like this, or contrast, and then you can say that they are uniformly distributed. Okay, that's another question. Somebody, okay, that's not to me. Okay. So then we have XPS for again this material. So then you can see the purpose for XPS again same, to know the oxidation states, and you very well understood till now this oxidation state can change at surface. And then also you understood the data of the XPS, whatever you know, the oxidation state, and X-ray, you know, XRD. That can be most of the time different, because XPS is surface study and X-ray is a bulk study. So X-ray is giving information from bulk, XRD. X-ray means XRD, X-ray diffraction pattern. And then we have electrochemical analysis for this material, and then this Faraday reaction, oxidation reduction reaction, and they are used to know this this behavior, CV behavior, and this information comes from again XPS. So all that discussion, this in XPS is used to know this nature of the oxidation reduction reaction. So we can know the oxidation states from there. And this is again a charge curve, and then a specific capacitance for this, and again stability. You can see after this much of cycles, about 1200 or more cycles, the stability is about 82%. Okay, so here, so nanostructure, we have again another material. So in this case, you have the particles. You can see here. Okay, so this is again, if you relate the morphology, whatever characteristic we understood, the good characteristic. One was the crystal structure. I am repeating again, crystal structure. Then was the size. Then was the morphology, and then pore size. Okay, again this size, crystal size, and then pore size. They are different things. Pore size distribution is also important. So these are many things, and depending on this morphology and the material, you can relate them how they are showing this performance. So I will not go these details because these we understood already. And then XPS purpose also we understood why we are doing XPS for different materials, and this electrochemical also we understood. So conclusion, let's make the conclusion for this particular part. So then you can see here, these are the two different material. One material giving monoclinic, other giving rhombohedral. Then you see La2NiFeO6, this particular material, and then monoclinic. Second material is monoclinic, and then we have La2. This is orthorhombic, Di2NiM, and this is monoclinic orthorhombic. But if you compare the different study, you will find a single material is precipitating in different crystal structures. And then what we talk about this doping, we can have a little bit of doping of other elements in these particular materials, whatever we talking about, this one here, we can have a little bit of doping. So that can still change the crystal structure, and we can have higher conductivity. So conductivity is also a very important factor, and that we discuss in between on various slides. And that conductivity, if you talk about the then different structure, then this cubic structure gives the better conductivity. So you can still try to precipitate in the cubic structure, but that is always not possible. So you can just try to be more symmetric. So that is possible always. So, but it is always possible to try to have different dopants and try to change the crystal structure and get the higher performance. If you, and then as per the summary, if you see the surface area, this is coming almost every is coming this between, all are coming between 2 to 50 nanometers. So mesoporous, everyone is mesoporous. You can see surface area, pore size is this. So pore size is always between 2 to 50. So mesoporous only, and this is the morphology. And then a summary morphology, a summary of the morphology is this. So you can see the very good quality of the morphology for qualifying that criteria, whatever we discuss, we synthesize. And this last slide, this about the various parameters, but we are talking about the good performance. You can see here. So then this material is again we synthesize copper containing, like here, and then both are materials. So 635 and 831 is a farad per gram specific capacitance. But if you look the without this cobalt, like this material is without cobalt, they are also the same efficient. Like see here. So it is totally possible to have the cobalt-free material. As we discussed, the cobalt is toxic and leaching in the solution. This is harmful. Everyone want to get cobalt-free. So it is totally possible to get the materials. And then so nanosensors, we will discuss a little bit quickly. So then nanosensors we can define two ways. So either size is nano size, or sensor is not in nano size, but it can probe the nano size properties. So either of them is true. I repeat, either the sensor is in the nano size and it can probe the bulk properties, then it's a nano sensor, or the sensor itself is in nano size, this vice versa. A sensor itself is not in nano size, and it can probe the nano properties. So that way is called nanosensor. If you check this human body, normally we call 5 sensors, 5 senses. And if somebody has more senses, then we call as extra sensory perception, which is not received by 5 organs, whatever. We have tongue, we have nose, we have mouth, we have ear, we have eyes, we have skin, touch. So these are the 5 sensors in the human body. And for every sensor, we have artificial sensor. Even you will be surprised that we have more than 5 sensors in a human body. Rather, we say that 5 sensors, but really we have more than 5 sensors. You can see fluid sensor and then many sensors. These are all sensors, and we have artificial sensor for them. So now if you talk about the different type of sensors available, you can see the many sensors are available here. Okay, color sensor, gas sensor, many sensors, proximity sensors. So sensor is a very, very important area. Nano is important area. Then we have nanosensor. That is very important area. And then we will have this effect in the coming lectures, including nanosensors and how to apply them, nanomaterials, how to apply them, how to increase the or enhance the properties, or how to use the sensor. Those kind of different properties or this strategies will be used in the sessions which we have in coming days and coming session in afternoon. So then this slide, particularly how important are the sensor, you can see again, this is talking about the smart world or a small village or any smart city. And now you see the sensors. Here, how many
तुरंत कहेंगे अच्छा ओके समझ let me start I am introducing myself बहुत कुछ शॉर्ट कर दिया तुमने बीच में कहेंगे now I am introducing myself बहुत तुमने शॉर्ट कर दिया
hello, please stop this.
No, yeah, now you continue, please, sir. Dear participant, I am requesting to you, please be sure that your mic should be unmute. Mic should be mute.
Yeah.
Thank you, sir.
Please mute your mics. Yeah. So this slide, I am not taking much time. I will finish. You have to join. 3-4 minutes. I will finish. So you can join the next session. So then you see the sensors everywhere. If you talk about the smart world, small places, or a small city, everywhere you need sensors. You check this slides every side. We have the air pollution, forest fire detection, or this water quality enhancing, the wine quality enhancing, everywhere, waste management, you check. So many sensors are required. So sensors is really, really very wonderful area for everything, for teaching, for research, everything. And then it also has the scope for everyone. Even you are simple material scientist, you are an electrical engineer, electronic engineer, everyone. It has area, computer scientist, everyone, it has something to do. You can work on a whole sensor. You can see here there's a bioreceptors. You can have the equivalent to bioreceptors, nanoparticles you have, so they can do the same thing whatever bioreceptors does. And then you can have in engineering included in this one, and then signal application. So this include everyone. So this is wonderful area, sensors. And again, this is some hidden area, like this is the chemicals. Look, so this is a testosterone, and this is dopamine, and this is oxytocin. So if you check these chemicals, and they segregate in our body, if you have the higher amount of that particular chemical, the human behavior changes. Indirectly, I can say that if you inject these chemicals in somebody's body or your own body, then you will have this effect enhanced. For example, this particular chemical, testosterone, this governs the desire. So the desire for something, it can be desire for any person, any individual, or desire for anything. And if you have higher number of this chemical, the desire will enhance. The same thing happens. For example, this is particular case of the desire for individual, and then the second case comes to the romantic love. So the chemical now changes. This is the dopamine, which segregates in higher amount. So suppose if you insert this chemical by injection to somebody's body, increase the amount of this chemical, so this desire will further enhance, or you reduce this chemical, the desire will reduce. And then again, this comes attachment. This stage is something like when individuals, they have babies. and then they feel more close, more family kind of orientation with the individuals. And then there is another segregation of the chemical, this oxytocin, and this chemical that have the bonding attachment with the families. And if that chemical is not there, the bonding may be very weak. If there is a more, and then bonding may be very strong. So this can be, and our purpose is we can design the sensors in the future. We don't have the sensors now, but this can be very good future study, like design the sensor to measure these chemicals in the body and then know the person's behavior. Then you can say how much amount means you can measure the different this emotional phases of the person. So that is also possible. And so this is the last slide. We continued, and this is something I am showing about my work. I supervise 2 students, 3 students are still working with me. An MTech student I supervise 18, and foreign intern also, German students I supervise in my lab in India. And similar to other universities, we also have the project to supervise. We also published one book, this energy harvesting materials, physics and system design with practical examples. And this particular review has been published in Energy Harvesting Journal by Professor Michael Lovelow. He's professor at Technical University of Berlin. And he says that this is very good book, very precisely written on this particular topic. He says that he searched about in Google with this word energy harvesting. He found about 60 references. And this particular book is precisely written on this techniques, energy harvesting techniques. And then there are several other activities we also keep involving. So thank you, and I can quickly take the question. And so please join this session at 11, this inaugural session. And then if you want to ask the question, this YouTube link I have already sent. Please join the inauguration session. So if you want to ask the questions, you can also ask the questions anytime you can, because we will have more sessions. So you can just note down the question now if you are late now. Yes, this PPT, and then yes, you are writing Dr. S.K. Suresh Babu, you are writing PPT is here. Then we will share the PPT, and also this one, this video will be available. Video presentation of this whole program will be available to you after the course is over. The link will be provided. So so AICT will also make this available to YouTube. So these all videos, my lecture, everyone else lecture. So this will be recorded. This is already getting recorded. So this will be available for all the participants. Even those who are not participants, they can also view these videos on the AICT website and YouTube. Yeah. Any question you can ask quickly, because you have to join the YouTube. We have 3 more minutes left. So you please, if you don't have the question, please join the YouTube link, which I sent you before. Yeah. So I can say you can leave. If you don't have the question, you can leave now. And please join the YouTube link. We are already late for the YouTube link. Yeah, so you can ask the question to me later in another session. You can write down the question anytime. You can ask. You can also email or whatever. Okay, thank you everyone. Let's go to the another session. Thank you everyone, YouTube. And then this session, after the inauguration session, the next session and other session, every session will start on the same link. So you please join 10 minutes before the session starts. So you have the timetable. Please check the timetable and you join according to timetable always. Thank you. Thank you. See you again on the YouTube link. Thank you. So this session is over. Formally, this session is over. So everyone is free to leave this session. Please join YouTube link. Thank you.